So I'm very, very glad to be here with you today and to have a chance to talk about the work I'm doing and other researchers are doing in TJ Watson at IBM. So I'm going to talk about cognitive revolution and how we move from data analytics to artificial intelligence. So what I wanted to say is that we are here in interesting times when we are actually on the brink of the next revolution, which is cognitive computing revolution. So what is a revolution? It is kind of major change in how people live, in the culture, in economics, in society. It's very disruptive. And there are longer term changes. There typically last from 20 years to 50 years to 70 years, starting with industrial revolution where steam engine changed the way how people manufacture things, to trains and to car and oil industry, then later to electricity, and then to also internet. So these always completely change, these new technologies change the way how people use technology, how people live, and they're very disruptive to society. So we are approaching something which is a cognitive computing revolution, using more artificial intelligence in a way that will change our life. So let's look at the history of computing, which started many thousands years ago with abacus. And then with Antikythera, which is very, very complicated. Actually, it took in Europe about 1,500 years later to kind of replicate it and use it, what all Greeks were using. Napier's road, then to various kind of mechanical computing and Babbage machines, to ENIAC in circa 1945, which is kind of frequently considered the first electronic general-purpose computing machine. Then coming to System 360 from IBM, which introduced mainframes and brought actually computing to businesses. Next important point I would say is Deep Blue, 1997, when there was a chess championship and when machine beat a human chess champion. Next remarkable point is Watson in 2010, which played a Jeopardy game. And so the question is, what is the next kind of significant breakthrough in computing, game changer? And those are learning systems like we are experiencing now. So I would like to here mention one quote that they said kind of in 10 years, digital computer will be the world's chess champion, from Simon and Newell. And they said it in 1958. So they were completely wrong, and they were right. They were wrong because they missed kind of about 10 years, their estimate. But this is something which absolutely happened. The computer did beat human champion in chess. So looking on the games for world and computing, games were always very attractive topic for computing because they're very regular. There are clear rules, and they can be measured how well they play. So they are always kind of very attractive challenge to build a computer which plays very well a certain game. So starting from 1996, when Deep Blue win over Garry Kasparov, he was very surprised. He didn't see that one coming. After first game he lost, he then really kind of tried his best. And the machine just beats a human if it's well built for certain problem, right? The next big breakthrough is 2010, 2011, when Watson was built to play Jeopardy. So now Jeopardy is a very popular game in US. I don't know how much it's known around the world, but it is very complicated, basically, because a question being asked is tricky. Answer has to be in form of the question. But the question itself is tricky, so you have to parse it. What is the meaning? What is this question actually asking? Then finding that answer and giving it in a very short period of time. I think it's 200 milliseconds is that machine has to process this all to be comparable to best human players. So since it is not kind of only one area, it's covering all areas of human knowledge. It is obviously a huge amount of data which needs to be quickly processed in parallel. There are possible different solutions. So what's happening in the background of Watson, it's kind of a question is passed, syntax is extracted, the search engines keep going. There are kind of multiple parallel, hundreds of parallel searches, which are then making their hypothesis. The hypothesis is then evaluated, how likely it is, looking for the evidence to confirm that hypothesis is correct. And at the end, from the most likely answers, those answers are graded with confidence. So the answers with the highest confidence is then proposed to, is given as a response. Also, you have to model the way of how risky your game needs to be. Are you playing safe, or you have to kind of take bigger bets in order to win the overall game because it's relative to other players? So there are many, many aspects to consider. That was really a breakthrough in way how computing is done, is with the Watson to play Jeopardy, starting from text recognition, language recognition, to question and answers. And that technology is taken into the IBM Watson for oncology to make Dr. Watson engine, which is going to help, which is helping doctors fight cancer. And I will talk a little bit about that later. So let's see how the sensory problems software, where are engines in comparing to human accuracy in the sensory problems. It has a long history. Humans were always very curious to build engine which will behave like a human in certain human areas, like speech or. So in 1962, there was a developed engine called Shoebox, and it recognized 16 spoken words. There were letters from 0 to 9, so you could operations plus minus, asking for total. So those are all within those 16 spoken words. So you would kind of ask, how much is 2 plus 7 plus 16, take away 20, total, and then the shoebox would give an answer. So over time, that was the first, obviously, speech recognition. Over time, speech recognition increased in its accuracy, and its error rate went down. So from 1995, which was not that far, that was not that long ago, 1995, it was 43% error rate, which is significant, right? It's a lot. But over the time, it kind of, through work of many researchers like you and I, it went down. And to kind of be now at 6.9 or 5.5%, which is as good as a human can recognize it. It's the human recognition of language as well. So looking across the two areas, image recognition and speech recognition error rate, we see that for a long time, they were kind of quite being constant. At some time, over time, they went slowly down. The image recognition was getting better. Speech recognition was getting better. They were about 25% error rate, about 20% error rate. So over time, those are the best labs in the world which were working on these problems. And they had all kind of quite similar results. And then in 2012, if you notice, for image recognition, something significant happened. It dropped significantly. And what happened there is that introduction of large-scale neural networks was the large-scale neural networks were used for these problems. And the error rate fell from 27 to 12. So it is huge kind of drop. And since that time, everybody is using neural networks for speech recognition, for image recognition. And we can say safely that today, these systems are as good in recognizing dogs and cats as human, or better in recognizing them. So we can say everything but done. So what is the next revolution? Well, what will the engines do Now when they can recognize the images on ImageNet library, they can recognize speech with high level of accuracy. So how we are going to use those engines? Are the evil computers going to take over human race? So we think that actually they are going to augment human cognition, so that there will be a collaboration of using skills of computer to help us in our day-to-day life. So machines and humans, we have different strengths. So what we can do is we have our expertise, we are self-directed with our goals, we have our common sense, and we have value judgments. Machines don't have any of these. What they have is they have digital knowledge, huge amount of digital knowledge that we don't. A large-scale math doing much faster, much better than we can do. Pattern discovery also much stronger than a human can do, and statistical reasoning. So actually, the thing is to use both of these skills complementary. They are complementary skills, and using those skills we do not have, but engine can offer us, we can then make better decision. Just a simple analogy, using GPS. I used to be without GPS, I was also quite good to find my way around, but many people were not. And with GPS today, everybody is everywhere, not having any problems. So this is one of examples how complementary technology helps us make our lives easier. So having such smart engines who are equipped with the knowledge and reasoning and data, we can make then much better decisions, both institutions and individuals. For example, selecting a college in the US, that is a huge deal, or financing education. There are so many options what can be done. Which one is the the best one for you? Which one is purchasing a home? What is the option? And then, of course, for the institution, those are from the finances to marketing and sales, operations, and to medical decisions. So opportunities are tremendous. Again, repeating, it is complementary, working together, using advantages of a machine to make a better educated decision, to get more data, to make better decision. I will talk a bit about healthcare and Dr. Watson, and I'm also currently working in Watson Health. This is focus of the company right now to see how can we use these huge cloud computing, artificial intelligence resources we have to promote healthcare. And this is from Watson Health, the mission statement I took from the page. This is what we are here for. We will serve as a catalyst to help improve lives around the world, help lower healthcare costs through the power of cognitive insights. And areas we are working that to apply currently Watson Health to focus is on oncology, medical image recognition, drug discovery, to name just a few. So I'll give a few examples. One is this Watson Genomics project, which we are working on. It is it analyzes genome sequence. It finds, in order to fight cancer, it has to find within that genome, it has to find a mutation of the sequence. So finding that mutation, which is likely to cause cancer, you can compare that mutation with similar other mutations for the cancer causes. And that is used to then determine the best treatment, because the cancers are all different, sensitive to different medications. They respond to different treatment. So by knowing your exact mutation, you can get personalized, targeted care in terms of the best medical treatment, which fights that kind of cancer. So Watson Genomics, as all the other examples I'm going to show, they run on a the technical platform run is cloud computing. Medical data are getting in cloud computing in a cloud. They are very carefully kept because those are medical data. They have to respect many compliance requirements and security requirements because they are very sensitive data. We don't want sensitive medical data to leak anywhere. We don't, because that's our privacy as customers. We want to not anybody know if we have any bad disease which will kind of harm us in the future for our choices and opportunities we are getting. So data is getting into the system, the genomics, the mutations are detected, and then those mutations are kind of mapped to the different library of mapped mutations, and from that the best treatment is proposed. On the other side, there's a huge body of medical research work. For a single doctor, it's almost impossible to keep up with all the papers being published and all studies available. And, but machine can, Watson can do that, kind of process all that data and extract information, which is kind of giving then at the end the best recommendation for treatment for a certain type of cancer. Here's another example that is about medical imaging for cognitive radiology assistant to kind of detect the stenosis in the arteries. Medical images are huge. Studies have multiple images. Some studies have up to 3,000 images. And those experts, radiologists, they have to look at so many images. It's very hard to notice that here at the top is this stenosis here at the end where there's this red dot. It's kind of after analysis. Plus, those images are huge. You have to keep them somewhere. It's a huge burden on your infrastructure, on memory, and to keep it. So with a cognitive radiology assistant, about 95% of images can be discarded because they are analyzed, annotated, and the problems are identified. So it's not that engine is doing diagnosis. It is just reducing the amount of work a human technologist has to have a look at, say, yes, this is a problem, on this is just fine. So, and it also reduces, increases effectiveness of a human because the fatigue of looking at that many images, how can you kind of possibly stay that focused for such a long time? Another example I would like to give here is for skin image analysis. This is just a little app developed with a demoscope so that people can track their own melanomas or question if this is melanoma, what I have on my skin. Basically, with this special lens, you could take a picture and do image recognition, comparison to other. You will see now two examples. One is for, this is just a normal mark on the skin. Nothing is, it's uploaded in the cloud, of course, and then the comparison of the to the prior images, to the knowledge library, which is kept in the data center in a huge library of images. And it says, oh, it is just a kind of a regular brown globule, most likely. So it is nothing, it's just pigmentation. It's nothing serious. And there are also a different example when the image is actually showing to not be actually that benign, which again, engine is not making diagnosis, doctor is making diagnosis, engine's in making recommendation. This looks dangerous, you better go and check with so again, machines are not replacing humans here, they are helping in directing, making better decisions. So these all new applications, so artificial intelligence, those image recognitions, they are posing tremendous requests on compute infrastructure. So they are kind of, for image classification, there are 10 to 18 flops of compute power needed. For speech training, they are in thousands of languages, 10 to the 7th hours. So they are hungry for new compute infrastructure, for new computers, for new compute powers, because size increased in requirement is over 100 times over the last 5 years. So we have a need for stronger computers. What will that be? Looking at the history and growth of computing performance, from mechanical to vacuum tubes to discrete transistors, integrated circuits, bipolar, CMOS, we're kind of running towards the end of technology possibilities. A gate in a transistor is down to 6 atoms, 5 atoms. So how precisely can you place if there are 5 or 6 atoms in a gate? And so this introduces about 20% variability from one transistor, what you wanted it to be, to what is actually realized. And it cannot be controlled at such fine atom level, kind of how many atoms are in any circuit. So obviously, current technology is coming to its end. How will we keep with this hunger for computing? What is the next technology? Is that carbon nanotubes, quantum technology? What are the new technologies coming? And if you ask for them, they will come. New compute infrastructure emerges. I would say it's not a clear winner yet, but there is so much activity in building alternative ways of computing. So I will give here just several from which are done by different colleagues in the research. Quantum computing, approximate computing, neuromorphic computing. I will talk a bit about quantum computing a bit later. Approximate computing, well, maybe we don't need all those bits for every calculation. Maybe we don't need 32 or 64 bits for every record for many computing, especially if you're calculating neural networks. Maybe the precision is not needed, so that's why it's good enough. That is just one example. It's of course not for all applications that can be applied. If we are launching a missile, I assume you want to be precise. Neuromorphic computing is to build systems which mimic neural systems of humans. So they are kind of mimicking the brain, mimicking the neurons in how they are calculating. So we have to come with some new solution for the calculation, for new strong infrastructure to satisfy needs of, and now artificial intelligence is the driver and asking for more compute resources. So what are these two pictures? What is, does anybody recognize the picture on the left? Yes. It's a punching card, and on the right, it's a DNA. What is similar for both of these? What do these two images have in common? Genes, yeah, but what do they carry? Sequences. They hold some information. Just in order to understand what they are saying, we have to know how to read it. And that is what is actually these all new compute approaches. They change the way how we should see and encode information in it and interpret it. So let's talk about quantum computing just a little bit. So in classical computer, every bit has two states. It's either 1 or 0. And so if we have n bits, we can encode 2 to the n states. And at any point in time, we know what is it calculating and what is its state. In quantum computing, 1 qubit can be either 1 or 0, but we can also superimpose additional state on it, so it's kind of in between. It's both at the same time. And having multiple of those qubits calculating together, you have all possible combinations of them being calculated at the same time. And then when you want to read it, they fold all in only one state. They cannot stay. When you open the door of a qubit to see what's happening inside, it folds either into 1 or 0. But so while you calculate with qubits, it has all possible solutions. When you check what is the solution, you get 1. of those possible solutions. So from all those possible, you get one possible solution. So this is kind of very powerful for very complicated problems, like breaking the keys, for example, understanding those encryptions, because it will give you one of possible solutions. You will get one valid solution. You will not get all of this. So this is kind of very strange way of understanding how to encode it, how to do the calculation. So currently, IBM offers 5-qubit quantum computer available via cloud, and you can go on ibm.com quantum experience, and you can try to play a little bit with those 5 qubits to see what can you calculate with that, and how can you encode it. So to try it a little bit. I would like to, I'm sure many of you are familiar with Society of Mind and Minsky, saying minds are built from mindless stuff, from parts that are much smaller and simpler than anything we'd considered smart. It's considered a work of philosophy, although that was not his intention to write a philosophical. He wanted to understand language and learning and memory and self-conscious, those concepts. So, but this kind of mindless stuff, is that not like a neural network, which is in itself, one neuron is really mindless. It has a very simple operation like addition of multiplication and addition of number of inputs and applying threshold onto it. So that's probably why the colleagues in research named this serverless power system Minsky. They made just recently in August, they did this neural network speed breakthrough. They built it with 64 Minsky systems, Minsky servers. One Minsky server has one Power 8 processor, and I happen to work on that one too, so just saying. Power 8 processor and 4 NVIDIA P100s. So 64 of those, they got a scaling for ImageNet, image recognition of 95%. They implemented 101 layer deep of a neural network, and created using Caffe learning framework. And with this, I will close my presentation and will ask for any questions.
Yes.
Okay.
Yes, some questions. Thank you so much.